Thanks for the invitation and thank you for the introduction. So before I start with the actual stuff, let me start with an outline. I'll go through the mathematical history very briefly when the model was defined. And the second point is to discuss a little bit about applications. And that's because for me, this is the first project I've been working on where I was actually inspired by more applied research. So I figured that would be nice. And then my entry point to this model was the Poisson cylinder model. So I want to say a few words about that. But then the main point is really the fourth, which is to discuss how long sticks behave in higher dimensions. And that will, of course, become much clearer when I get there. And then in the end, if I have time, but I don't really expect to have time, I'll say a few words about uniqueness. Okay, so mathematical background. The first paper that actually introduced the name stick percolation was by Rahul Roy, and it was written in '91. Although it was sort of implicit in an earlier paper by Hall, I think from '85, because in that paper he gave various, so he studied a general class of continuum percolation model, and the stick percolation model happens to be one of them. So the Roy variant of this model is a two-dimensional model. Now, clearly, it's supposed to be about higher dimensional stuff, but I will start in 2 dimensions and work myself up. And in 2 dimensions, it's easy to define. Well, it's easy in all dimensions to define the model, but you just start with a homogeneous Poisson point process in the plane. I'll show you some slides, some pictures after this slide. And then at each point, you just place a stick, and in his variant, he gave it a random length, so independent, but for all the line segments in the picture, they had independent lengths, but he did require uniform bound on the lengths. And then he also gave them a uniform orientation, so you can think of them as just being spinned and then sort of landing on some sort of random orientation. Okay. So here's a picture of what it looks like. Here lambda is small, and what you're seeing is basically a bunch of isolated sticks like this, although a few of them hook up and they form like components of more than one stick. But of course, if you increase lambda, you get more sticks and they start forming bigger and bigger components. And as you increase, it's very believable that in this picture, if you think of this as being extended in the entire R2 plane, you will be able to find unbounded components. So you have this phase transition, conductivity phase transition, if you like, or percolative phase transition in lambda. So there's a non-trivial critical value lambda c, so that if you're low intensity below lambda c, you have just finite components, but if you're above, you have unbounded components. Now, this result was actually not due to Roy, because this was already from the previous paper by Hall on this general class of models. But rather Roy, he focused on what's known as an RSW result. And if you don't know what that is, that's fine for the rest of the talk. It stands for Russo-Seymour-Welsh. And it's a type of tool that's really important when you look at planar percolation models. And he used that to study not just this lambda c that I explained above, but other various critical parameter values. You could look at, for instance, expected cluster size instead of the existence of an unbounded one. And you get another critical value, and he was able to show that these are in fact all the same. Okay, so that was 91. But after that, it seems that stick percolation has flourished within the physics and chemistry communities, at least outside of my knowledge up till recently. And they're using it to model loads of different stuff. And please don't ask me about details here, because I don't know the physics or chemistry enough. But thin film transistors is basically a 2-dimensional model. And we all know what a transistor is. They also study microelectronics, microelectromechanics, and optoelectric and photovoltaic devices. The latter one here, photovoltaic, is basically solar cells, I think at least. But of course, for their point of view, a 2-dimensional model purely like the one by Roy isn't very natural to study. So Rather, they look at sticks, which are basically long wires or needles, very thin and long. And they, of course, live in three-dimensional space. And some of the inspiration, I just name drop a few papers here. There's one by Mieta Negri and Tamborenia, and there's two by Tarasevic and Eser Kepov, which are nice and have a lot of lists, applications and things like this. They're all based on Monte Carlo simulations. Okay, so I wanted to have a concrete application in mind, so I sort of dumbed it down a little bit and maybe made it a naive one, so I can understand it myself. And the one that I went for was the following. So I think of having what they call nano-wires, and again, it's basically needles. I fixed the length for all of them to be the same, L, which is maybe unrealistic, but I wanted to dumb it down. And they all have width 1. And I think of them as being maybe made out of copper or some other material that conducts electricity well. But then what we do is that we suspend them in, say, foam that sets and hardens. Something which is very lightweight. So what you do is then you create a composite material consisting of this heavy needles, which conducts electricity, but they're suspended in this lightweight thing. And of course the foam doesn't, it's insulating, so it doesn't carry any current. But then the goal is to create a composite material that's still conductive but lightweight. And for this to happen, you have to have large components. So as a mathematician, I basically think of this as being the existence of unbounded components, or that we're in the percolative phase. But of course, these wires, they're long, but they're thin. And so it's interesting to figure out how, sort of what density of needles do you need in this mix in order to get the composite material to be conductive, and how does this depend on the length of these needles? Okay, so that's the application. Next step, I'm going to the Poisson cylinder model. So since this was my own sort of entry point into this stick project. So I'll be very informal here, because there are some technical details when you want to define the Poisson cylinder model that I'm just going to ignore. But intuitively, it's easy. You just think of it as a random collection of cylinders in RD. Let's take the width of all the cylinders to be 1, and they are now by infinite. And this collection is invariant under, so if you take the picture and you translate it, or you rotate it, or you reflect it, it statistically looks the same. And classically, continuum percolation models are a different flavor. What we typically do is that we take a point process and we throw out balls, or maybe rectangles, maybe ellipsoids. They can have sort of random diameter, they have some distribution, but typically they're all bounded. But this is different because here the objects themselves are unbounded, so you can't really talk about, you know, unbounded components, because just one of them is unbounded in itself. So here's a picture of what it looks like. I've taken a box in three-dimensional space and then simulated the cylinder model, and then take the intersection of the cylinders with this box. So it looks like a chaotic mess of needles or cylinders. And summer of 2019, I bumped into a colleague, Arthur Lee, at a conference, and he's also working on the Poisson cylinder model. And he showed me this picture. So he had been to the Smithsonian Museum in Washington, and he found this quartz crystal with impurities known as Schorl inclusions. And they sort of look a bit the same, like you're taking a Poisson cylinder model and you're just restricting it to this crystal. And it's sort of nice to show this, I think, because it tells me that some of the stuff that looks, you know, maybe strange when you simulate it actually almost at least appear in the real world. Okay, so many people have worked on this model, and it's a bit egotistical. I'll just cite one result, and it's by myself together with Johan Tykesson, who Tobias also mentioned in his talk. But it's because it's the one that's relevant for this presentation. And We studied the collection of cylinders, and we managed to prove that the collection is always a connected set. And it doesn't matter what the intensity is. And what that means is that if we go back to this picture, let's say you take a cylinder here, and imagine you're an ant living on this cylinder down in the corner, and your wife or your husband lives on this cylinder, and you want to go and visit your husband or your wife, and you're only allowed to crawl along other cylinders. Then the result just states that you're always able to do that. It doesn't matter if it's a sparse sort of model with not so many cylinders, or if there's loads of cylinders. It's always connected. We actually proved something which is a bit stronger, and that is that the diameter is always d-2. And that means that in the case of dimension 3, you can always go from your first cylinder to the goal cylinder by just using one other cylinder. In 57 dimensions, then you need 55 other cylinders, perhaps. And also, you can always find a pair of cylinders which has this distance. So the distance is d-2 for that pair. And again, it doesn't matter what the intensity is. It always looks the same. So it means that this cylinder model is sort of really super connected, right? I mean, it's not just that you have unbounded components, you have that trivially, but rather everything is connected to everything else. So it's really super connected. And then knowing about the stick paper by Roy from before, I figured it probably was natural to look at what happens at the sort of the analog of stick percolation model in higher dimensions, and study what happens as the length of these sticks diverges. So I think of these as being larger and larger. And just in case we forgot about the model, I'll just repeat it. This is actually a variant of it because the sticks are now slightly different in length and width. But again, you just start with a homogeneous Poisson point process in RD, and the intensity is again lambda. And then at each point, you put a cylinder segment, which I call a stick, and I fix the length. I mean, you can do variants where you take random lengths, but for now, I just figured I'd stick with the simplest model as possible. And also the width I fixed to be 1. And then again, I give it a uniform orientation. So I just take a point on the unit sphere, and that sort of corresponds to the direction of the stick. And again, of course, this is done independently. The orientation is independent for every stick. All right. So then I consider the union of all the sticks, and that's my occupied set, or my set script C here. Of course, I expect there, and it's sort of almost trivial now with modern tools, to prove that there's a non-trivial critical value. So you have a phase transition, which is interesting. So there's a non-trivial lambda C, which is such that if you're above lambda C, then you percolate, which just means that the sticks form unbounded components. But if you're below it, then you have no unbounded components in your picture. Now, clearly, if I think of L here as being something big and as diverging, it's sort of easy to understand that lambda C must depend on L, right? Because if you start with a subcritical model with short sticks and then you let them grow, eventually they're going to hook up and they're going to encounter other sticks and they're going to form unbounded components. So lambda C has to depend on L. And so more precisely, the question I sort of posed before, more precisely becomes the following. Can you find some alpha that can depend on D, and which is such that lambda C of L is roughly L to the minus alpha as L diverges. And if you can show the existence of such an alpha, you can ask what is it, and of course, how does it depend on D? Okay, so that's been the study of my Corona project. And before I give you the result, I'm going to start with the intuition in 2 dimensions. So again, I'm not in high dimensions, I'm going back to 2, but it's because the intuition works very well there. And in 2 dimensions, if we look at the simulation here I've I'm saying that the length is 2, but you can think of this as being much longer than the width, which is what I'm drawing. But the reason why 2 sticks are touching each other, like these 2 here, it's not because they sort of get close-ish, but it's because they actually cross each other like this. And so it shouldn't really matter whether the width is 1 or if it's 0, because the connection is made by the center lines crossing of the sticks. So width should not be important, at least when L is large. Okay, so if we accept that as a fact, even though I'm just hand waving, then yeah, we can see what happens. So I then take lambda to be larger than lambda C of L. So that means that this picture that I'm showing extends to an entire space R2, and it contains some bounded components, right? And then I rescale space. So here I let L be equal to 2, and I rescale space, not just the sticks. I'm not just shrinking the sticks, but I'm rescaling everything. So I'm rescaling space now by a factor of L to the minus 1, which is then in this particular example 1/2. And that gives me the model, the stick model where the length is 1. But of course, then the intensity is now L squared times lambda. And that's easy to see from these pictures. This is the original one. If you look at this void here, it also shows up here. And in fact, this black box was this previous slide. And in the same size box, I now have 4 times as many sticks roughly. So this is the scaling. But then since I just shrunk space, if I was supercritical before and I had a unbounded connected component, I obviously still have it because I'm not changing any connections. So this means that L squared times lambda is strictly larger than lambda C of 1. And then I just move L squared to the other side and I get that lambda is larger than L to the minus 2 lambda C of 1. And the nice thing with this intuition in 2 dimensions is that it actually works fine also in the other direction. So for this variant of the stick percolation model that Roy used, where the width is 0, I can actually obtain the equality that lambda C of L is exactly equal to L to the minus 2 times lambda C of 1. So I get the alpha and it's minus, it's 2 in dimension 2. This is, of course, for sticks of width 0. And then you can ask, well, okay, but maybe this intuition works in all dimensions. So sort of maybe it works the same, but that's not true at all. And the reason for that is that in 2-dimension, width is sort of not very important because of how they touch each other, 2 sticks. But in higher dimensions, they're absolutely crucial because it follows from the Poissonian nature of the process that the probability that 2 center lines of sticks intersect is 0. 2 sticks intersect because they sort of just touch each other, not because they actually, the center lines are touching each other. So while width is irrelevant in 2 dimensions, it's the only thing that matters sort of in higher dimensions. Not really, but you understand what I mean. Okay, so the intuition doesn't hold. Then what is the actual result? So the main result of sort of a work in project, but almost finished, is the following, that this alpha equal to 2 is actually universal. It doesn't change with the dimension. It's true for every D. And the exact statement of the theorem is the following, that lambda C of L can be bounded from below and above by taking a constant, little c, which may depend on D, times L to the minus 2, and this is the lower bound for lambda C of L, and then I have the upper bound with just another constant here, which may also depend on D. Okay, now the proofs I have, they do give some estimates on these constants, but I expect them to be far from optimal, so I'm not really bothered with getting clean expressions for them. Okay. Now, for the rest of the talk, I'm going to just sketch the proofs. So all in all, I think the written down version of this is maybe around 25 pages, but it's one of these results where The idea is fairly easy to explain, and it's amenable to drawing pictures. So I hope this works. The lower bound here is by far the easiest. The majority of the work comes from the upper bound. So let's start with the easy one, the lower bound. And it's sort of a classical argument, this one. The idea is to couple the stick process with a subcritical branching process. And the way you do it is that you start with a sort of a base stick, S0, and I think of this as the root or generation 0, if you like. And after that, I start exploring the sticks that I see. Now I'm drawing it in 2 dimensions, but this works equally fine in 59 dimensions. And I start exploring the stick process, and then I find some sticks that intersect my first or my base stick S0. The number of sticks is clearly random, right? And it's easy to understand that it has to be Poisson distributed. And if we call them S11 through S1n, well, then I can think of these sticks as being the offspring of generation 1. And the expected number of offspring is then just expectation of n. So n is the guy that I need to look into a bit more careful. Now, the next step, you have to do something more, right? Because if this is S11 and I start exploring this stick and looking for new sticks that intersects this guy, I'm not allowed to find a stick which intersects S0 because I've already explored S0 entirely. And I know that I just found 3 sticks. So that means that the number of sticks that hits S11 in my next step of the exploration is some n tilde. And n tilde can be quite complicated, but luckily it's easy to see it has to be stochastically smaller than n. So in the coupling with the branching process, you just throw out n tilde and pretend that it's n. It has the same distribution. Okay, so that explains the coupling. Now you just have to figure out what the expected value of n is, and that is not too difficult. So here's for once a stick with where I actually drew some width. So the width is the vertical spacing here. And if this is a long ball and it has length, long stick and has length L, then you can basically think of it as being consisting of a bunch of balls of diameter 1 like this, these blue balls just lined up after each other. Clearly, if I look at the sticks that hits this ball here, that's going to be dependent on the guys that hits this ball. But luckily, if I just treat them independently, I get a bound that goes in the right direction. This is why this is the easy part of the argument, basically, because I can just pretend I have independence and it just goes in the right direction. And then I just take one of these balls and I try to figure out what the expected number of sticks is that actually hits this ball. So here's the black dots here are points of the Poisson point process, and these are the sticks. And the dashed ones are missing the ball, but the full one here hits it. And then you do a bit of calculation and you see, well, that has to be of order L. So you conclude expectation of n is bounded by the number of balls in a stick, so the number of blue balls here, and then times the expectation of the number of sticks that actually hits the ball. And you get L, lambda, CL, and then you get your upper bound. Okay. So you have an induced branching process, you have a bound on the expected value of the offspring, and so if lambda is smaller than this CL to the -2, this branching process is subcritical and it dies out almost surely, which means that the component of S0 is finite almost surely. And then from that, it's easy to show that the probability of finding an unbounded component must be 0. So that gives the lower bound. Okay. Now, the upper bound requires more work. And it's a geometric construction of an unbounded component. And it's done by coupling it or comparing the stick process to what's known as oriented percolation. And oriented percolation was introduced by Rick Durrett, I think late 80s or maybe early 90s. And he used it to prove results about the contact process. And that turns out to be very useful here. Not the contact process part, but the oriented percolation. And so in order to explain what goes on, I have these red squares and this blue square here. But really, you should think of this as happening again in high dimensions. This is not a two-dimensional argument at all. And I'm placing these in d-dimensional space, so with the same distance between the boxes. And the side length of these boxes are of order L. You should think of them as being, say, L divided by 100. So the stick here has length L, and these are sort of the same order, but much smaller. And the blue boxes, they are used to hunt for center points for sticks. So I'm trying to look for a point here, and then a stick that actually has that point as a center. And I also wanted for this construction in the first step to be almost horizontal. And what I mean by that is that it has to exit this red square here on the right-hand side. So it has to be centered here, and it has to exit down there. And if I can find such a stick, then I'm happy. Because on that stick, I can find these black balls. These are basically the same as the blue ones here, but they have some, they're separated by some fixed distance, say 10 or 20 or something like that. And I think of these as being a string of pearls, and they are displaying targets for the next step of the construction. And the next step looks like this. So then I take another blue box just above the red box here, and I'm hunting for center points of sticks in this blue box. And I tried to find one of these, and I needed to hit one of these pearls, these target pearls. And I also needed to exit the top part of this red box here. And that gives me an almost vertical stick that presents a new string of pearls like this. And then I can proceed. So I can try to go to the right, and then I can try to go to the left. And if I keep doing that, you get this picture, which looks a bit messy. But here's again the base stick. You're going up almost vertically, and then almost horizontally to the right, and up, and then to the left. And the thing is, and this is the majority of where the work actually is, and I'm of course just brushing that under the carpet, but the thing is that you can prove that if lambda is larger than some constant times L to the -2, then the probability of actually finding such a connection like this is as high as you like. So say 0.9 or something like this. So if this actually occurs, and now I know it occurs with good probability, 0.9 say, and if it occurs, then I draw one of these solid arrows like this. So then I found a connection from here to here and to the left. So I have a solid arrow here, and I can go from this up to the left. So I have a solid arrow, but I couldn't actually find a connection going, sorry, to the right I meant before, but I couldn't find a connection going to the left. So that's why I have a dashed arrow here. Okay, so this clearly induces then a model, which happens to be the oriented percolation model, and which looks like the following. So this box is replaced by this vertex. This box up here is replaced by this vertex. And the fact that I can find a connection that goes shoop shoop, that gives me an arrow going from this vertex to that one. Okay, and that's the oriented percolation model. And you can extend this, you can look at this then in the entire upper half plane. And then I'm lucky that Tourette was there a couple of decades before me and proved that if the probability of finding such an arrow is close enough to 1, then this creates an unbounded component with positive probability. And because of the coupling with the stick process, I know that if the oriented percolation process has an unbounded component, then also the stick percolation process does. And so this gives me the upper bound here. Okay, so I see I've been talking now for close to half an hour, so I think it's a good place to stop. Thanks.